Hello and welcome to the Cyber1 YouTube channel. My name is Ray, and in this video we're going to start our journey into the world of networking. Before we get started, thanks go to my #1 Patreon, Go Lucky. And don't forget to subscribe, ring that notification bell, and click on the like if you like the video. Links to the Patreon and my Discord are in the description, as well as a few other video series I've done. So let's get started. Back in 1984, the International Standards Organization, the ISO, released the Open Systems Interconnect OSI reference model. So yes, the OSI was developed by the ISO. The model was broken down into 7 layers. Starting at the very top, closest to the user, you've got layer 7, the application layer, the presentation layer, the session layer, the transport layer, the network layer, the data link layer, and finally the physical layer, the actual wires, so to speak, in our networks. In this video, we're going to concentrate on the physical layer, and the next one we'll look at the data link layer and work our way up. I probably won't go much into the layers above layer 3 or layer 4, mostly because we're dealing with the physical network within our robots rather than the software side of it. We will talk briefly a little bit about it, but not all protocols use all the layers. The Modbus protocol, for example, uses the RS485 physical links, and it misses quite a lot of the upper layers. So let's have a look at the physical layer. All networks have a way of transferring data, normally in binary form, from one physical device to another. This is known as the physical layer and will consist of 2 or more wires or a radio signal. When we look at different types of physical layer, each was designed with a particular goal in mind: speed, simplicity, distance, reliability. Now, I just want to talk about the two or more wires. In this definition, ground is considered to be one of the wires. But there are some physical layouts where a ground is not required because we're measuring the difference in voltage between 2 different wires, where if the voltage is greater than, if wire A is greater than wire B, it's a logic 1. If it's less than wire B, then it's a logic 0. And that's known as a differential system. One of the things we need to be aware of when we're looking at our networks and designing networks even is capacitance in wires. Now, a capacitor, put simply, consists of 2 or more parallel conductive metal plates, which are not connected or touching each other, but are electrically separated, either by air or some form of good dielectric insulating material, such as wax paper, mica, ceramic, plastic, or some form of liquid gel. The symbol for the capacitor is basically 2 plates with wires connected, and a separation between those 2 plates, as shown in the bottom of this image. As voltage is applied across the dielectric insulator, current will flow and charge up the 2 plates, positive on one and negative on the other. The amount of charge that builds up is proportional to the area of the capacitive plates and the voltage, and is inversely proportional to the distance between the plates. The value of the capacitor C is measured in farads, and is the charge able to be stored in the capacitor divided by the voltage of that charge. So we can have a capacitor with multiple plates in it, as long as the plates are connected in such a way that the area sums up to give us 2 plates. What if we look at our wires? We've got wires that run a distance, and you could almost consider those wires to be 2 metal conductors. Well, they are 2 metal conductors running in parallel to each other, separated by a plastic dielectric insulator, with a surface equal area to half the diameter. It's actually half the circumference of the wire multiplied by its length. So yeah, we have a small value capacitor. The longer the wire, the larger the value of that capacitor. And in some installations, those wires run together pretty close together for quite a distance. If you have a look at your average network cable, they're very, very small wires in those, and they've got very thin insulation between those wires, and they can run up to 100 meters. So yeah, you can get quite a bit of capacitance there. Slew rate is one of the things that we don't like in our network cables, and it's the rate at which the driver device on the network can increase or decrease the voltage over the entire length of the network cable. The longer the wires, the greater the capacitance, which I mentioned earlier. The other one that's a lot of people forget is the longer the wire, the greater its resistance. The larger the wire diameter, the lower the resistance, but the greater the capacitance, because you're increasing its circumference. Now, this is where things get to be a little bit tricky, because when you increase the length of the cable, not only are you increasing its resistance and its capacitance, and if you increase the resistance, the longer it takes to charge the capacitor, in this case our wire, and so the greater the slew rate. So the longer we make our cable, the longer it takes for the voltage level to change from, say, a low to a high or a high to a low. And this limits the maximum possible speed we can transmit at. So typically with a long haul, like a 1,000 meter type RS485, you end up having to drop your transmission speeds back because it takes longer to charge the wires up. The other problem we can suffer from with our physical layer is interference. Data is normally transmitted as a stream of bits, ones and zeros, and electromagnetic waves from other equipment or environmental factors can flip bits, corrupting the data. There's two ways we can combat this. We can prevent the signal from being changed, layer 1 type stuff, or we can detect and or correct the errors at layer 2. So we'll talk about layer 2 in the next video, and we'll talk about how we can try and prevent the signal from being changed in layer 1. Interference will quite often come from devices emitting large amounts of electromagnetic interference. Things like motors, or wires carrying power to motors. The three-phase supply quite often to the BLDC motors that we use in robots and the like will carry quite a significant amount of interference. Things we can do is reduce the length of the wires. The longer they are, the more likely they are to pick up interference. Complementary signals is used in some of the different protocol types. So RS485 uses complementary signals, whereas RS232 doesn't. As a result of that, the RS485 can be used at 100 times the distance of an RS232. The other thing that can help is twisting the wires, and in some cases twisting the wires at different rates if you have parallel sets of wires within the one cable, and that's what they do with network cables. If you actually strip the outer casing off a network cable, you'll actually see that each pair within the network cable has a different rate of twists. Twists per inch if you like, or twist per foot if you like. The other good method is to try and shield our wires. Now there's also a little caveat with shielding wires. If you're going to shield your wires, only connect the shield at one end. If you connect the shield at both ends, you can create loops, what we call an earth loop, and a current can flow through that, and if you have a current flowing, it will generate a magnetic field, and magnetic fields can induce currents into other wires, such as our signal ones. So you only earth at one end. Now the next one that's a real problem and very, very difficult to get around is reflected signals. When a device transmits a signal over a long signal path, the transition from low to high and vice versa, the signal travels along the wire at close to the speed of light, and when it hits the end of the wire, it will produce a reflection that then travels back and forth in a reducing pattern. Remember, the wire has a resistance, so it will reduce that signal with the resistance within the wire. But over long runs, this can cause issues with it impeding the current signal going on the line. So if you've just sent a logic 1, you can have a ring down occurring. Now, while you hold a logic 1, that's not an issue and it will ring down reasonably quickly. But when you switch to a logic 0 immediately after going to a logic 1, so if you're transmitting if you've been transmitting a 0, you transmit a 1 and then you transmit a 0 again, the reflected signal can superimpose as a 1 on top of where your 0 is supposed to be. And this becomes more problematic with the longer runs. It's very hard to spot these issues until you put an oscilloscope on and you can actually see it in the oscilloscope as small spikes in the wrong direction, not of the same amplitude of what you're driving the signal at. But it can cause interference with the detections. Now there's a couple of ways we can try and mitigate this problem, and the most common one is to add resistors at the ends to bleed that voltage down to ground. The other method is to actually use transformers at the ends and actually look at current flowing. You don't need much current with a transformer. You just need some. Like if you use a larger turn ratio transformer. And the RS485 protocol, or standard, actually says to use 120 ohm resistors at each end to help reduce that. If you look at the 10100 network in the category 5, when you look at the equipment, inside the equipment after the RJ45 socket, you'll actually find there are transformers on the boards. They're usually little black packages containing a couple of transformers, and they're used to do two things. One, ground out those reflected signals, and two, provide a level of isolation between the pieces of equipment. In the Power over Ethernet standards for Ethernet, they'll actually center tap the transformer on the wire side, and they'll use one pair of wires for your positive and the other pair for your negative to actually provide power over those wires. You can't get a lot of power with the Power over Ethernet in this physical network because the wires are physically small in diameter, and so they don't carry much current. So typically they'll run around the 48 volt mark. In a lot of countries, once you exceed 50 volts, you need to be a licensed electrician to work with them. So to prevent that, they run below that level, and they run very little current. So you've got to be aware, if you're designing a piece of equipment that will be powered over Ethernet, it has to use very little power because there's very little over the Power over Ethernet. Okay, there's quite a number of standards in physical networks. The RS232 has been around since the 70s, early 70s, late 60s. RS485 was developed, a short time after that. It was actually a version that was developed from the RS222, which later became the RS422, but they didn't really take off. The RS485 did take off because it was considered to be a multi-drop network. One wire was developed by Dallas Semiconductors, and that one uses a ground and one signal wire. but it supplies both power and signaling on that a single wire. It's a half duplex format. I2c, a lot of us with our Inmoov robots will have seen that one used in places. SPI, those familiar with the Arduino will have seen the SPI interface. Ethernet 10100, if you've got a computer, you've seen that one. And Wi-Fi is a very common one. And yes, Wi-Fi is considered to be a physical network, but more on that a bit later. So the RS232 doesn't have a long range. It's, around about the 10 meter mark. Once you get over 10 meters, it starts to suffer terribly from interference. And so it's usually just a connection between an end device and your computer at a very close range. I haven't seen many cables for modems and the like that are more than a meter. Now, there's quite a number of wires used for data, not all of them with the DB9, but in the DB25, they actually had two sets of transmit and receive signals and a few other control wires as well. But normally you have a single wire for receive, another one for transmit, and these are supposed to work around the 15 volt mark. So you can see where charging the wire up to a higher voltage also creates issues. You've got the ready to send, clear to send, data set ready, data terminal ready, detect, carry detect. So when a modem is actually seeing a carrier on the phone lines, it can assert that line if present. There's also a ring indicator, so if a modem picks up that the phone's ringing, it can also signal the computer. Now, this is old technology, and we don't see it being used very often anymore. A lot of systems will simply use the RX, the TX, and the ground. Some will optionally use the RTS and the CTS, or the ready to send and clear to send options to help with flow control, but most systems are doing the flow control in software now. Now, the other one that you may have heard of is Ttl Serial, and Ttl Serial is like RS232, except it's usually 5 volt logic levels, and the signaling is actually inverted by comparison. With the RS232, a logic 1 is transmitted as a 0 volt and a logic 0 as a 15 volt. Now, where I said the RS232 has a range of around about the 10 meter mark with our cabling, TTL logic is not even that. You're lucky to get a meter before you start getting a lot of interference on that one. The RS485 I touched on earlier, this one comes as half duplex using 2 wires because it's actually a complementary wire system or complementary signal. That is, when one wire goes to a logic 1, the other one will show the opposite, a logic 0. So you can have and it usually runs at around the 5 volt mark as well. So when you're transmitting logic 1, wire A will be at 5 volt and wire B will be at 0 volt. When you're transmitting a logic 0, wire A will be at 0 volt and wire B will be at 5 volt. All we need to do then is actually look at the difference in voltage between the 2 wires, and we're just looking for which one's positive, A or B. If A is positive relative to B, then it's a logic 1. If B is positive relative to A, it's a logic 0. Now, if we use 4 wires, we can actually get full duplex. And this system's always a master-slave system. So the master will transmit on one pair and the slaves will respond on the other pair. Now, under the rules of RS485, you cannot have 2 slaves responding at the same time. So generally the rules within the protocols will specify, only a slave will only respond if spoken to by the master. And a good example of this is the Modbus Rtu Protocol. with the Modbus Rtu Protocol, no slave is permitted to transmit unless it's instructed to by the master. So the master will typically send a request out and then the slave responds. The master's instructions are it's not allowed to send another request or command out until such time as either the slave has responded or a timeout period has occurred. Now this is a point-to-multipoint system because we can have one or more slaves connected to the network. You will always have a master on one of these networks as well. The RS-485 protocol is specified to run up to 1,000 meters, which is handy for factories, and it uses a pair of terminating resistors on each pair, one at each end of 120 ohms. In our one wire, we use a 4.7k ohm resistor connected between the 5V DC system and the data line. Now this will supply a small amount of power onto the data bus, and so devices such as the DS18B20 temperature sensor can use this to power the temperature sensor. Some of you may have already seen these sensors. They typically come with 3 wires coming out of them, a red, yellow and a black from memory. Black being the ground, the yellow being the data wire, and the red can optionally be connected to either 5V supply or left open circuit, not connected to anything. When they're actually running their analog digital converters from the temperature sensor for the controller, they sometimes require a bit more power, and so the device or the bus master, usually our Arduino, can actually drive that line higher by turning its input to an output and turning it to a logic 1, supplying extra power to drive that conversion. So the way these ones usually work is the master, our Arduino, will send the command, do a conversion. Usually it will send it to be, or send the command to the bus as a broadcast, so it can talk to multiple devices at once to tell multiple devices hanging off the bus to start their conversion, and then it'll drive the bus to a fairly high power level. At the end of that time, it will then go back to having it as an input, and it will send the command to an individual sensor, report your result, and then the individual device will return that signal or return that data. And it's a master-slave system. The slaves are not permitted to return data or control the bus in any way until such time as they are told to do so. And only one slave is permitted to operate the bus at a time, or the master for that matter. The data wire is normally held at logic 1 or positive 5V, and a signal is transmitted by shorting that to ground. It's a very simple system. It relies on a consistent timing which is set within the protocol, and it will send a stream of bits. All transmissions are started by the master, so it will send first the command to return data, and then it will send the start signal by transmitting a 0, pulling it to ground for a short time and releasing it again. The slaves then transmit by pulling the line to ground again for each bit that they need to transmit. In this way, we can have multiple devices hanging off this bus, and each device is got a it was either 32 or a 64-bit address. So you shouldn't, these are programmed in at the factory, so you shouldn't get two of the same address. And I've actually run a one-wire system with 6 devices on it, no problem at all. I believe you can get a lot more on there, but once you start to get too many devices on there, you need to seriously consider running separate power supplies. The I2c Bus is used very commonly in our robots as well. If you've been following the Fred build series, you'll know that I run I2c right throughout the robot for all of the servo controls.
Again, the I2c is a master-slave system. It transmits 8 bytes of data, or 8 bits of data in byte format, and uses 2 wires for the control. We've got the SDA and the SCL. Now, like the one-wire bus, we use pull-up resistors at each end. The pull-up resistors do 2 things. 1, they help eliminate reflected signals, and 2, it allows the slave or the master to send data by pulling the line down or shorting it down against the resistors. Data is presented onto the bus, and then the clock signal is pulsed for each bit of the data. Returning data is also clocked by the master, not the slave. This is also a point-to-multipoint network. That is, the protocol that is transmitted, the sequence of data that's sent, contains an address. So the master will send to an address, please respond with this data, and then the slave is permitted to respond with it being clocked by the master. In the SPI serial peripheral interface, now I haven't used this one much, but it does use 4 wires in actual fact. We have the master out, slave in, master in, slave out, and the serial clock from the master. We also have the chip select, or the device select. Each device that you have on the SPI network does require a separate device select line. So the number of pins that are used by your microcontroller is very much dependent on the number of devices you have connected to the SPI network. So you've got 3 that are required just for the communication, and then if you've got 3 devices connected, you need another 3 pins to select the devices. It is a full duplex system. That means the master and the slave can transmit at the same time. In fact, it's part of the protocol that they do that. In this case, data is presented onto the bus by each device, master and slave, as the polarity, or as the clock transitions from one side to the other, from low to high or high to low, and it's then read on the other clock edge. The orientation of this signal is dependent on the protocol that's being used. So some will use a positive edge to clock data on and a negative edge to read it back. Others will use it the other way around. So yeah, go back to reading the manual on the SPI protocol before you start using it, so you know what you're doing. The 10100, it's now being phased out. It'll be around for a very long time still, and it uses 2 pairs out of a 4-pair cable. Most of us would be familiar with the Cat5e cable. It has 4 pairs of wires in it, typically blue, orange, green and brown. And we actually use pairs 2 and 3 out of that cable. And they're normally connected to pins 1, 2, 3 and 6 of your RJ45. RJ45 is actually, I think, more of a brand name than anything else, or a part number from a brand. The correct term is actually P8C8 connector, which actually means it's got 8 connectors with 8 wires, or 8 pins in it. With the gigabit coming through now, they actually use all 4 pairs. This is because they're actually splitting the signal up and they're sending it as 2 bits at a time, parallel. Now, it is a point-to-point system. It is not a multi-drop bus. You can only have 2 devices on the one cable. You might say the master and the slave, although that doesn't really suit here. They're both able to transmit on the line at the same time, and they're both able to receive. If you go back a long time with the Ethernet 10100, they used to have hubs, in which case it was a half duplex system and you could only have 1 device transmitting at a time. Most Ethernet 10100 systems use the collision detect method. That is, they would watch the line and they would transmit, and if what they received while they were transmit didn't match what they were transmitting, they called that a collision. They generated a random delay, and then they would check the bus to see if it was being used and then start transmitting. The reason for the random delay was if two devices were trying to transmit at the same time, in theory one of them should get on before the other and they just wait their turn. It was very common for use with hubs, but the advent of the modern switch eliminated most of those problems and also sped up the networks quite considerably. Now, our final type of physical network is a little counterintuitive. It's radio. It's a signal that's being transmitted across the air, and Wi-Fi is one that everyone would be familiar with, but there are other radio-based networks. You may have heard of Zigbee. There's a couple of other mesh-based systems as well. LoRa is now starting to come into common use, and some systems will use the 433 megahertz frequencies to transmit data at low rates. And these can be considered a point-to-multipoint system. That is, you can have a master, which is controlling your network of devices, and you can have multiple devices that they talk to. Again, it all comes down to the protocol, and there's a lot of different protocols out there. So that'll do for this video. Don't forget to click on the subscribe, ring that notification bell. If you like these videos, there's a lot more information to other videos and the like in the description. I have got a Patreon account. There is a Discord that you can go in and ask questions, and others or myself can answer those questions, or you may even be able to answer some that others are asking in that area. So drop into the Discord and say hello, and we'll see you in the next video.